So, hello after the short break. I hope you could get some coffee to refresh, and we continue now with the second part of the lecture. So again, a standard question, can you see the slides and can you hear me?
I don't see slides.
Brilliant. So now we will move on to some discussion on using we're putting basically what we learn into practice and see how can some digital or analog signals be actually transmitted. Okay, so first of all, we can have that's the basic classification. So I hope this is more of a reminder for you. So we can have a
Excuse me, because we
yes.
still can see the slides.
Oh, you can't. Wait a second. Yeah. Lovely. Now this should work. Can you see it now?
Yes, now it's good.
Brilliant. Right. So basically, just a general classification of signal types. So they can be periodic or aperiodic, which basically is embedded here, right? So with the periodic signal, it means we get a certain period t0 over which the shape of the signal repeats itself. This is, the most common example we will use is the sine function, well known. Contrary to some aperiodic signals, again, the common example would be what's called a noise or white Gaussian noise, right? Which is okay. And then again, another classification is whether a signal is deterministic or stochastic. Right, so basically deterministic is it's a signal that can be described without uncertainty. So again, our sine function would satisfy this property. Whereas a stochastic signal, we can describe it only in terms of certain probability, right? But overall, we cannot really say that certain value of the signal will be present at a certain time instant. And again, the main characteristic is noise, right? Yeah. And usually, of course, in practical applications, we will have the combination of all of them, right? Because you cannot operate. So typically, we have a sine function. However, you would also as you hopefully know from the part about modulation, you would very often have a sine function that is, looks the same from minus to plus infinity, right? So this periodicity can break a little bit here, and also you would almost always have some noise on top of your signal, right? So you take everything into the mix. We can also think about the signal, of course, as analog and digital, with hopefully, so basically analog signal deals with signal where both amplitude and time are continuous, whereas with the case of the digital signal, amplitude and time can have a discrete values out of a countable set, as you see here. So again, I hope this is more a repetition from the signal theory. However, in our context, in the digital signal, the important factor is, of course, that we need to discretize our signal not only with respect to different values, but also with respect to the time sampling. Okay. So how can we do this? Well, the first approach is to do some sampling in the time domain, right? So over here we got our analog signal that changes continuously, and of course the full analog signal is very challenging to handle or very difficult to use. So nowadays, of course, most of the systems, telecommunication systems at least, would be digital, with maybe like a really few exceptions. So what we do, we have our continuous analog signal, and we discretize it with samples that are usually equidistant in time. So, right. What is important here that this is we still have like a continuous possibilities for amplitude of each of the sample. So for the time being, we just with sampling we just cut and time or move the time from the continuous towards discrete sets. Now the question is, we of course want to do it without losing any information. So how can this be achieved? Okay, well, we need to make sure that our sampling frequency, so distance between the time samples TS as shown here, is dense enough to capture all relevant information, right? So how this can be done? Well, here comes what's called the Nyquist-Shannon sampling theorem. And this is basically like the cornerstone of digital electronics, basically, or electronic systems. So this is again the same Shannon, which named after the same Shannon, which came up with information theory. So he did quite an impressive amounts of work. Okay, so basically so typically when we have the signal that is limited in bandwidth with a certain frequency FU, with U stands for upper. Right, so we know that whatever shape of our signal is, it's typically of course periodic, right? But it does not contain frequencies which exceed our FU, so our upper frequency. Well, in that case, how we can our sampling should be simply double the sampling frequency and or twice the FU, or in the contrast that corresponds to the 2 samples per period. So this pretty much means the same. And such a signal can be unambiguously reconstructed from digital back to analog. So again, we are not losing any information here. And why actually double the upper frequency? Well, hopefully this this graph here can illustrate the principle. So over here we have the red curve, which is the signal, the sine function that we try to sample. However, as you see here, we are not really satisfying the Nyquist-Shannon sampling theorem. So we're sampling only one sample per each period of the sine function. All right, and with that in mind, once we are done with the sampling, we transmitted the sampling data, and the receiver tries to recover our information recover the original signal, right? And what hopefully you can see that if you just take the set of the black dots over here, right, without the information about without satisfying the Shannon sampling theory, or without the information about the upper frequency, you can see that there are actually more than 2 signals that could perfectly fit into that curve, right? So at the end of the day, we don't really know which one of those 2 curves are being transmitted, right? However, if we actually do apply this principle, and we know a priori that the sampling frequency was indeed double the upper frequency, or that there were like at least 2 samples per period, well, this actually means that out of these 2 possibilities, we can remove the red curve, simply because it doesn't satisfy the sampling frequency, and we end up with the blue one, right? So the ambiguity in that case is removed. So hopefully this is a very simple principle. It can be also explained, so this is explanation from time domain. Later on, if we have some time left, we can also look at analogous reasoning from the frequency domain point of view. Okay, but basically the rule is that you need at least 2, when discretizing the time, you need at least 2 samples per period, which corresponds to sampling frequency double the highest frequency of your signal, and then you can recover your signal without losing any information. Is that clear? I ask because this is really one of the most important concepts that we are discussing here. Okay, so basically what I would like you to remember is that if you're waking in the middle of the night and somebody asks you, I don't know, what is the sampling frequency of a signal with upper frequency 10 gigahertz, you should instantly reply 20 gigahertz, so double that. Okay, so Nyquist Shannon, that's really important. And this is a little bit visualization of what happened in the frequency domain if you don't don't satisfy the Nyquist sampling. We have something which is called frequency aliasing. Okay, so basically this this got to do with the fact that the discretized signal in the frequency domain will be basically seen as an infinite series of copies of the spectrum, right? So basically when you are, so this is your origin, the spectrum of your original signal. And when you basically add the discrete interpretation of the signal, you create all around the spectrum multiple copies of this. So this basically means that if your sampling is again less than double the sampling frequency, you would have a thing called aliasing, which means a portion of your spectrum will overlap, or 2 portions of the signal will overlap. And then again, it's difficult to distinguish whether this is like the upper frequency part of your signal or the aliasing of the lower part of the aliasing copy of the symbols. This is something that should be avoided at any cost, because that's easy way of when you lose information. Okay. By the way, a typical approach here is, or typical example of aliasing that you can very often see in movies or in action movie, or next time when you see one, you can actually pay attention to the helicopter blades. Okay, and basically on most of the movies, you will actually see that the helicopter blades are very slowly rotating in the opposite direction that they are in reality, right? And this is exactly because of aliasing. Okay, so what's happened there is, I believe with movie you got 32 frames per second, which is of course much lower frequency than the real movement of the helicopter helicopter blades, right? And the consequence of that is the same as in this curve, that to our eye, when we see the blades, it seems on the movie that it is moving very, very slowly, as opposed to the real movement. It's just because the sampling of 32 or even whatever sampling frames per second there is, it's significantly slower than the frequency of rotations of the blade, and that's the effect you can see on the movie. So just next time you're watching any action movie or what, you can pay attention to that. Okay. Now, an important solution to the aliasing is to use the low pass filter, which would allow to protect your original signal. However, the low pass filter can be used again only when you do the proper samplings, when there's no overlap or different signals. We see how that works in a moment. Now, we spoke about sampling, so discretizing your signal, analog signal, with respect to time. Now what we have to do is some quantization. So typically the process of quantization is when you discretize also the amplitude of your signal. Okay, so or basically that's some more formal definition, right? So we transform continuous amplitude to some set of discrete value out of a finite set. Okay. Okay. And contrary to the sampling, the quantization is a non-reversible process. Okay, so this basically means that once you do the quantization, you're always losing some portion of information that's there. So you cannot fully reconstruct your signal. Okay, and this is again contrary to the sampling, when I said you can use the Shannon-Nyquist theorem for proper sampling frequency to avoid that problem. But that only works with periodic signals in time domain. With amplitude, you cannot do nothing, and hopefully we'll see why. Right. So those are typical functions of quantizers. So over here we got continuous input, and this input is translated into set of discrete steps, discrete output of the quantization. So in that case, it's 1, 2, 3, 4, 5, 6, 7 different steps. Well, you can of course do what's called round towards zero, which means you round the discrete value towards ceilings. Sorry, towards zero. Round downwards, which means it's reduced. Well, I mean, whichever you choose, that's different surges. You should be aware there are different types of rounding here. Okay. And also what we can do, very often we can opt for non-uniform quantization, and there are just some complicated equations here. So basically they won't show up on the exam. The important message here is that you can, in terms of quantization, you doesn't need to be always uniform. So for example, you might like to have more steps for signals of a low amplitude and less than steps for signals of high amplitude. And this is something that is represented by different shapes of the curves here. And this is also called compounding. So compounding is a word which is well, compressing and expanding. So for example, we have a original signal like this. It's a sine function, of course, with increasing amplitude. And after compressing, you basically amplify lower values without affecting that much the higher values. So you end up with a function like this. And then when you quantize such an expanded function with a non-uniform quantizer, you might have better, you may better capture the properties of the signal that you want. Okay. So anyway, as I mentioned, the quantization is a non-reversible process and leading to quantization error. And hopefully this graph here should explain why. So again, on the top drawing, we have the analog signal, which is the blue curve, and then it gets quantized with the red curve, right? And you can see that we are using some rounding. We lose small portion of information here. And this is what is called quantization error, right? So the error, the missing part of information is here. And we will, not contrary to the sampling, we won't be ever able to recover that information again. So once it's lost, it's lost. Okay. We can try kind of to change or reduce this information loss. And here's the example of the errors with two types of quantization. One is a uniform and the other is non-uniform. So hopefully you can see here that with the non-uniform case, we have much denser steps for the low signals. So up to, let's say, amplitude 1 in arbitrary units. So basically we have level Z. So here we have simply one quantization at each level. So 1, 2, 3, and 4. Whereas here for non-uniform quantization, we have one step over here, which is, so it's maybe better seen here, which is half. Then the next step is 1, 2, and 4. Right? So what this means? Well, this means that for a strong, very good signal, we typically have a larger error. However, we capture the signal much better with lower error for the small values. Okay, and in certain cases, actually, this might be really advantageous when you, for example, think about quantization error. If you want to capture like small signal variation of some weak signals, that might be beneficial over here. Okay, so with that, we move on to the digital transmission, right? So the pulse code modulation. And over here, we have some analog signal, and we want to transmit it using, some digital communication system. So, classical example could be, for example, voice, which is transmitted digitally over certain channel, right? So basically based on what we just discussed, there will be, as you can see here, the holes. So 4 different steps starting from our source. And it will combine discretization in time and as well as quantization. Okay, so can you tell me maybe, or try to guess, of course, what will be the first step here in moving basically from the analog signal into digital one? So okay. So again, when you transforming analog signal into a digital form, what is typically the first step you should do based on what you just showed in the slide? Again, I write
Sampling or filtering, maybe?
Yes. So which one of the two?
I guess it would be better to sample it after we filter it, so...
Yes, exactly. But and the next question that follows is why?
To avoid some spikes or values which shouldn't appear because they're noise, so we don't want them in our signal. I mean, in samples, because they would cause distortions.
Yes, you are. You're going in the good direction. So basically, so yes, this is partially correct. Basically, the sorry, the reason is to avoid aliasing. Okay, so
yes, as it was said before.
Yes, so basically, if you take any signal, well, firstly, there will be a noise which has infinite spectrum. Also, if we're talking about like acoustic radio signals, it may have some higher frequency components, okay? And after you do the sampling, those components actually will leak into the bandwidth, into your bandwidth, and they will cause distortion. So first thing, we apply low pass filter. Okay, what should be basically the sampling frequency with respect to the low pass filter here? Or what should be the sampling frequency with respect to the bandwidth or frequency, upper frequency of our signal?
It should be 2 times higher.
Exactly. So basically, the low pass filter is more or less the same as the frequency of as the upper frequency of our source signal. I say more or less the same because you might need to allocate some time for the slope of your filter. Then we do sampling. Then we do quantization, right? And then at the end, of course, since we are talking here about the communication, we do some coding, right? So adding some information into the we start to process the channel. So basically, just to put some numbers into this work, we assume again here the human speech, which has a limited bandwidth of 300 to 3,400 hertz. So sorry, what is the actually what is the sampling frequency of such a signal here?
Um, 6.8 kilohertz.
Yes, exactly. So I'm going to cheat a little bit, and I will take a little bit higher, so 8 kilohertz. This is just mainly for the ease of ease of calculation. But okay, then so we did the sampling, and then again, of course, with this sampling we can have the filter at even up to 4 kilohertz, right? So this 8 kilohertz, that's actually just some rounding that I did, but it's not necessary, but there will be some oversampling basically here. Then the next step, we have the quantization, and because of the requirement of the systems, we assume that each sample needs to have 256 one of 256 discrete amplitude levels, right? So then what does it mean? When 256 discrete amplitude levels, it means for the coding, we will have as an input 256 different words. which is basically 8 bits, right? So 8 bits here, this is understood, of course, as bit in the binary case. So 0 or 1, a set of 2-letter alphabet. Okay, so basically to put all that together, we have, in that case, 8,000 samples per second, right? Each sample encodes 8 bits, right? Which results in minimum required communication speeds of 64 kilobits per second. And that's, just a simple multiplication really, right? So you take the analog signal, you sample that with double the frequency, and then depending on how much quantization you want to have, how much quantization do you want to have, this will be, of course, typically power of 2 for binary signals. Then you do coding, generating, a code of 256 words, which is 8 bits per word. So you multiple frequency sampling by the number of 8-bit words. Is this? I hope this is more or less clear. Okay. So bear in mind here that this is actually signal really before it enters channel coding, right? So typically the 64 kilobytes per second, that's just for transmission of your signal. If you want to add some redundancy, right? So for instance, single bit parity check, the simplest one, this would change from 8 bits per 9 bits, okay? Which would correspondingly, change your calculation over here. So this is requirement of how much kilobits per second you need to transmit certain signal, and typically this would be benchmarked with the equation on Shannon-Hartley theorem that you saw in the previous slides, which deals, with the bandwidth of your signal and or available bandwidth to your signal and your signal to noise level, right? So basically, if your digital communication stream is 64 kilobits per second, your channel capacity needs to be at least that much to avoid errors. Okay, and bear in mind that because for many telecommunication systems, we in the modulation process, we are actually changing the frequency that we are operating. So in principle, this is what we call the baseband frequency. It's not necessarily the same with the bandwidth that you saw in the equation for channel. Okay. So for example, if you have low signal to noise ratio, you can try to compensate that with lower bandwidth. We'll go to that in a moment. Now, are there any questions towards this? Okay, I see there's not. So now we move on to a process what is called oversampling, and that's actually something which I did in the previous slide by rounding this 6.8 kilohertz into 8 kilohertz, right? So I used actually much higher sampling frequency than is necessary. And this is exactly what is called oversampling. So basically you put more samples than the minimum amount you need to. Now, what do you think is the name for that? Actually, that we talk later on today in the slide, or how this can be labeled in different terms using the information theoretical approach. So what is like oversampling? Oversampling is just one form of what we talked earlier. And basically oversampling leads to redundancy. Okay, because again, you are embedded, you are using up more information than the minimum necessary. Okay, this basically means that the neighboring samples of the signal are strongly correlated, right? Because the signal changes little, and there is a form of predicting, what is the next or the previous sample from the previous one. Okay, so again, you get oversampling, you get some form of redundancy, and with little difference variation between signal itself, right? And this is something that again is adding, transmitting more information than you need. However, again, in certain conditions, you might like to do that to combat some forms of problems with channel. Okay. So this is hopefully clear that this is also a form of redundancy of transmitting more information than you really need to. And if you do a lot of oversampling, basically your system is not efficient, right? Because then you transmit a lot of bits which are correlated with each other. So basically there's, again, little of this variation, little of surprise effect. You can very easily predict next or previous sample with respect to the previous one. However, you could also, reuse that information for error correction, right? Because since you can predict the next sample from the previous one, it allows you some way of, interpreting or correction if you see a mistake. Okay. And then again, removal of oversampling of that information allows for more efficient coded signal, right? So basically, what I'm trying to say here is that this is all like implementation of the informatical of the theory of information approach that we saw earlier, right? It's just a different manifestation, and it doesn't, the redundancy doesn't really need to take this, primitive form of simply repeating multiple times the same bits, right? It can be also done with sampling. All right, and going back to the previous equations, hopefully you can see that I use here 8 kilohertz, but if I would like further increase the sampling frequency to, let's say, 10 kilohertz, right? Well, basically what happens is with 10 kilohertz, I need more bits. So from 64 kilobits per second, I would move on, let's say, to 80 kilobits per second if we assume 10 kilohertz. However, we are transmitting still the same information, right? So the required communication stream increases, but again, it's still the same signal. There's nothing new, right? So that's the point of efficiency here. Okay. Redundancy. Right. Now, I wanted to tell, how much time do we have? Oh, okay. I think actually we're running a little bit out of time. So, right. Actually, okay. So let's do this part. It's again some form of reminder, but so okay, just to make sure we are on the same page, is more or less those concepts of sampling, redundancy, oversampling, and Shannon-Nyquist PCM code. Is it more or less clear? Are there any questions? Okay. So here actually comes the part about the signals. I should maybe do this before starting about the Sony, but okay, basically this is considered to be a repetition of some basic signals. So theory, so hopefully you know that we have some sort of signal or periodic signal that can be characterized with linear speed, angular speed, and so on and so forth. That's basically a sign. It can be described by hertz, which is number of periods per second, right? And that's more or less how it works. Okay, now you should be familiar by now also with the Fourier transform, right? So typically what's happening here is that when we have a perfect sine function, so that's 1 kilohertz going from minus to plus infinity, and you do the Fourier transform. So you look at the frequency spectrum, it will basically be seen as a Dirac delta, right? So just one single peak, which is infinitely narrow, basically. However, with a finite integration. Now, okay, and this is basically typically a general rule for most of the time and frequency transformation. So typically, it's a bit intuitive approach that I hope you will get. If we think about the time signal that is very long in time domain, so well, in this extreme case, of course, sine function minus to plus infinity. When you do the Fourier transform, you will have actually a very narrow signal. And actually the vice versa approach holds, right? Because you should know that apart from the scaling factor, the Fourier and inverse Fourier transform, they're symmetric, right? So if you would have a time signal, which is Dirac's delta, in frequency domain, you would have a bit strange, but spectrum like this. Now, if we consider the sum of two sine signals, we can add them, right? But then in the frequency domain, here you should be still able to separate them, right? And in this case, of course, this might seem trivial that it's a sum of two sine function. However, if you add noise, over here it's much more difficult to see what the signal is all about. So you cannot see really, the frequency by naked eye. However, if you do the Fourier transform, you still see the two dominant peaks, that's the two signals of your component. And here you can add the noise. Okay, so why the noise is here? So the noise has much lower amplitude, with the difference between the signal amplitude and noise amplitude we seen as the signal to noise ratio that we spoke earlier on. And of course, the white Gaussian noise, so-called, the basic model for noise, it's considered to be frequency invariant, right? So you will see it all over, all your frequencies. Now, I hope that's should be more or less repetition. So the only important factor is that the spectrum or Fourier transform is actually represented by a complex numbers. Okay, and again, that means that we can have an amplitude spectrum and also a phase spectrum. Now, usually, of course, in most basic analysis, we are more concerned about the amplitude spectrum, and that's what you would see on most of the plot. However, again, you shouldn't forget about the phase component. And in practical terms, when you have the in time domain, you may have two signals which look totally different, and they will have the same amplitude spectrum. However, and will differ only by the phase spectrum. Okay, so and vice versa, like the signals in frequency domain which have the same amplitude spectrum and different phase spectrum would be seen as two totally different signals in time domain. Like, I mean, completely different. Okay, just some reminder again. So we know we have a rectangular pulse, which is like a perfect rectangle with here. And then again, when we move from time domain to frequency domain, again, bear in mind it's just amplitude. You will see what's called a sinc function, right? And basically again the narrower your rectangle, the more wider will be your frequency spectrum. Okay. Similarly with step pulse function, so they produce a certain things. We're talking here about a perfect rectangle, which is not practically implemented, right? And why? Well, because the perfect rectangle would require, a jump, basically, so a sort of discontinuity. And such a jump, as you should know from the principle that I mentioned earlier, will actually require your spectrum to be literally from minus to plus infinity. And this is simply something that we cannot realize with electronic circuits. So we are always like bounded by a certain bandwidth that we can use in telecommunication systems, which means such a jumps are not really possible. So it always be a certain slope of the signal. Okay. Yeah, and that's basically just a repetition of what I mentioned earlier. And here's actually the part that why I'm actually bothering with this. Okay, so now we are moving to a spectrum of periodic signals. However, we are concerned with periods, different than signals different than sine functions. So we have this, idealized rectangular function, and we try to approximate it by a superposition of different sine function, which is exactly what the Fourier transform is doing. Right. So, well, here in the first approach, we just have one sine function, which, well, simple sine function. Then we add two, right? And we can see that with the two different sine function of two different frequencies, it starts resembling more the rectangle that we're having here, right? It's not perfect, but we slowly see that it's getting there. So what do we do next? Well, we add the third sine. So, sorry. Over here, you can see more and more resemblance, right, to the desired function of the periodic signal that we have here, right? Then we add the fourth, one more, and it's still, we are approaching closer and closer to the rectangular function. But as I mentioned, we will never really have this perfect rectangular slope. And so can you maybe tell me how many sine function we would need to add to have this perfect rectangular shape? How many different sine function of different frequencies?
Infinite.
Exactly, right? So that's not going to happen. But you will always have some sort of a slope and some sort of this behavior. Now, looking into the periodic signal again, any periodic signal. Okay, I think I'm stretching actually my time a little bit right now, so I propose to stop here maybe and continue on the next lecture. That might be actually a better idea than rushing with the things I want to explain to you. So again, are there any questions, any concerns, or? Or
could you maybe explain the numbers on the slide, which was about the sampling of human speech audio? It was quite, yeah, it's quite a long way back. So, because it was like 256 discrete amplitude values, which is 2 to the power 16, I believe. No.
Okay, so okay, actually, maybe I will.
2 to the 8. So where do these numbers come from? I mean, 256, and then the code and 8-bit words.
Yes. So okay. So right. So basically, the 8-bit word, it simply comes from the fact that we have 256 discrete values. Okay. So basically, to show 256 discrete words, each word will require eight bits. And that's simply it, right? It's basically 2 to the power 8 means 256. So in that way, bit is interpreted not in the information theoretical aspect, which is confusing, but simple as a row of zeros and ones. Okay, and the rest it's just a simple multiplication, right? So
okay,
right, okay. Sorry, okay. I believe I'm a bit confused. I think what time we're supposed to finish the lecture? Because now I actually think do we still have half an hour left, or? Yes. Oh, sorry. I think I was confused a bit by the time change. So anyway, any other questions in the meanwhile? Okay. Sorry. My mistake. Right. So. Okay, so let's continue where we left and with the signals. Right. So now what's okay? We are trying to reconstruct this perfect signal. We know this actually not possible. Okay, now I mentioned earlier actually that there is a symmetry between when we move between time and frequency, and typically when we have the perfect rectangular filter in frequency domain, the same principle but reversed is applied. So basically, we cannot have a perfect rectangular filter simply because it would require a signal which goes in time from -infinity to +infinity, right? And we simply usually cannot wait that long with our signal processing. Okay, so this is another reason why typically when you use a low-pass filter, any type of filter, it will never be like a perfect rectangular filter. There will be a filtration slope, right? Which means depending on how you design your device, certain signals can leak into your signal from the edges of the slope, right? So and that's exactly the point where your oversampling might be sometimes also beneficial. Simply, if you have a low order filter with not very steep slope, then you can combat that by adding few samples more. Okay. Now, when we move to the periodic signals, well, typically when we have the periodic signals, it will generate certain harmonic frequencies, which are at the multiplication of basic repetition frequencies. So for example, if you have the rectangular pulse here, right? You can actually, it will be like, of course, superposition of infinite number of sine functions for a perfect sine. However, the frequencies of the sine function will be located at 0, f, where f is the period of your signal here, and multiplication, natural number multiplication of that signal, and that's what's called harmonics. Okay, and that will be true for any signal, regardless if it's a triangle repeating itself, short pulse, or square repeating itself. Of course, the shape of the spectrum will be different, but you're always like generating the signal at the harmonics. And well, the more harmonics you take into account, the more your signal is relevant. Now, why am I talking to this? Because this got also a relevance for the sampling. Okay, because if you actually think about that, the sampling is a periodic signal of, or quasi-periodic really, but just the sampling frequency is, it turns out it changes your continuous frequency domain signal into a set of superposition of discrete number of frequencies. Okay, so typically you will, when you apply sampling, you will see that the spectrum of your sampled signal, which is basically can be seen as a row of Dirac delta spaced by sampling intervals, will hypothetically move from 0 to plus infinity in the row of like that, right? So, and this is the reasons why what I was trying to tell with the aliasing query. So I just should go back. Apologies for this. Right. So when we speak about the aliasing, okay, we know that again this is our analog signal, which it has a bandwidth which ends over here, right? And basically, when we have the sampling, by sampling frequency, we will create multiple copies of this signal in frequency domain, which will be stretched from minus plus to plus infinity, because we are adding like a periodicity to our signal. So the same principle that you saw earlier will apply. Now, the problem is here that assuming this is our maximum frequency, our sampling frequency will be double that. So, somewhere here. And this basically means that when we create the multiple copies of the spectrum of the same signal, they will be created next to each other, right? And then again, when you do, recovery of your signal, you can apply low pass filter, easily get rid of all the aliases, all the multiple copies of your spectrum, and recover your original signal. All right. However, if you do not satisfy the Shannon-Nyquist sampling, you will experience aliasing. So basically, the multiple copies of your spectrum, which generated due to sampling, will overlap each other, right? And this, as you will see, will alter your signal and will cause you some ambiguities, so basically you will recover that signal with error. Okay, so hopefully this is pretty much clear. So those are the this here, what I'm trying to explain with this twice sampling per period, And the aliasing, when you do this sampling, this is pretty much the very same thing, the very same phenomena. Just once we discussed that from the time domain perspective, and the other from the frequency domain perspective. But of course, they kind of converge to the very same thing, and right, and they're basically the same. So right, so right. Any more questions relating to the signal, or I hope it wasn't too quick when moving on to the time and frequency switch here.
I have one question.
Yeah, go on.
So we have Nyquist Shunt Huron. It's really impossible if we will sample some signal and we are not meeting this requirement. But if we would like do it for we're sampling it for a long time, or just like trying to shift the sampling frequency, it's really impossible to get like good idea what the real signal looks like.
Not really, because if you are if you're sampling for a longer period, you're still kind of sampling in not good enough, right? So in the sense that I'm just looking, right? So over here, if you look at this plot over here, right? If you sample for a longer time period but using the same frequency, you can see that you'll just get more of the same, right? So this is actually not a solution here, right? Because it doesn't really solve your problem. And so in terms of moving the frequency, this is a little bit tricky, right? Because but in principle, so this theorem in principle deals with the signal in what's called baseband, right? So by baseband we mean low frequencies which are closer to the 0 hertz, right? So for example, if you think about the Wi-Fi signal, right? Wi-Fi signal is around 2.4 gigahertz, right? And that of course doesn't mean that we are sampling, that your router samples this signal with 4.8 gigahertz. Okay, so basically what happens is it's got to do with the fact that basically you are occupying only 20 megahertz around 2.4 gigahertz, right? So basically that from, let's say, 2.4, well, 2.4 minus 10 megahertz, let's say, there is a lot of frequencies where there is none of your signal, right? So in that case, what you would do, you would take your signal, convert it from the Wi-Fi frequency of 2.4 to the baseband, which would be 20 megahertz, and then apply the sampling with the 40 megahertz Nyquist. That's how it would work. I'm not sure, is that what you were asking for, or does that answer your question?
I know what we are talking about, but I mean that if we don't have aliasing, and we will change the sampling frequency, we would still have the same signal. But if we have aliasing, then what we see from the I think it's called sin x on x, then this is what we see. For example, on oscilloscope, would change with the sampling frequency.
Yes.
Or not.
Yes. So basically, when you increase sampling frequency, you get rid of the aliasing.
Yes.
Right. Yes. But that's exactly the same principle, right? Because when you increase it, you're moving into this, ideally to this, Shannon-Nyquist frequency or above, actually, and that's why you get rid of the aliasing. Okay. Right? Does that satisfy you?
Okay.
Okay. So now we have a little bit more time, actually. So let's move on to some right. Basically, some analysis of the telecommunication system. So just putting a little bit more of what we learned about so far about error correction, error detection, and so on. So basically, again, this is our well, we specified that in this case it's a digital communication system, and pretty much it's the same graph that we show earlier, with the difference that in that case we've so we broke up the coder into encryption and compression. So normally those two components would be part of our source coding or source coder. The coder is the channel coder, the modulator channel noise, and the reverse process happens on the receiver, right? So again, just a bit to summarize the terminology that we discussed. So firstly, when we speak about data compression, right, this is used to decrease the amount of transmitted data without decrease of transmitted or significantly decrease of transmitted information, right? And where the significant is in bracket, it's of course because of the quantitative and qualitative compression. So in terms of quantitative, this is lossless, like zip format. In terms of qualitative, we have some information loss, such as JPEG, right? And this is something done with the source coding. So again, quantitative compression, it simply removes the redundancy of the information. So we are approaching as close as possible to the theoretical limit, which is given by entropy. Whereas in the case of qualitative compression, we can introduce some changes into the signal, which we don't really care that much, right? And in that case, we sometimes can slightly go even below the theoretical limit, which means information loss. Another thing which we haven't covered so well is the encryption. So basically, the encryption, this is something that we add to our signal to ensure confidentiality, also for authentication and integrity of information. Now, we won't talk a lot about encryption in this course. However, I would like to state the distinction between encryption and encoding, okay? Because there are two totally different terms. So typically, when we speak about classical cryptography, it changes the information into a form that can be understandable only for someone with a proper key. With the key can be symmetric, asymmetric. That's a bit different story. Okay, but basically the encryption, it's the information content in the encrypted signal is actually the same as before the encryption. It's just less understandable. Okay. And then, of course, the content is transported back in the decryption, but only in the presence of a unique key. Okay. Okay. Now, again, in terms of coding, we have the channel coding, which is used to ensure sufficient communication quality. It introduced some redundancy, which is later used for error correction. And then the modulator, this is, as we said, some physical change in the physical signal, which allows us to encode information. Okay, so and it can also be seen that the modulator, it is changes or maps sequence of symbols into the set of signals. And the demodulator again does reverse process. So again, I hope this is all clear to you. And then also actually going back to what we speak earlier about forward error correction and automatic repeat request. So there are these two approaches. One is simply, we have a binary input, you have a channel coder. And in this case, your channel coder, of course, embeds more redundancy into the code. The communication moves through channel, and then the channel decoder performs, error correction. And this is what's called forward error correction, simply because, you're trying to, in advance, anticipate the type of errors that may appear in your channel and combat them with channel coding. Right, and on the other hand, if you don't have error correction, but only some error detection coding, this of course allows you to be much more efficient here, so you don't add that much data. But then of course there is the repeat request protocol. So basically at the channel decoder, there is error detection, and there is the repeat request sent back to the source. Now, this is of course not 100% correct, because obviously this repeat request will also need to go through the channel, right? So sending that repeat is actually a bit more complicated than just this, straight arrow here. So such a request is also an information by itself, right? So it would also need to be coded in order to make sure there is no the request arrives safely to the desired form, and it has to travel through usually the same channel as the original information. Okay. Now, for the different types of codes, this is just a basic characterization. So we are referring here only to the channel code. So types of codes basically which are used, to increase the redundancy. And basically, they can be divided to the nonlinear and linear, right? So this, of course, defined with respect to mathematical operation, right? So nonlinear code will leave that a little bit behind, but the most commonly used typically are the two types of linear codes, which is block codes and convolutional codes. So how do they work? Well, basically the block code is the most simple code, where we have a stream of communication. We chop that stream into a block, hence the name, and we always perform information only on the single block of information. Now, contrary to this, convolutional codes, they basically continuously process the data stream, and it applies something which is called the sliding coding, which basically hence the name convolution. So basically, those codes would apply the convolution operation between the data stream and the transfer function of the code that we are concerning. Right. So basically, the information is not treated as a separate block, but rather certain amounts. It's like a moving or sliding. Okay, and of course, it's discrete signals. So we're talking about discrete convolution. Now, here I want to go back to the channel capacity, which is given by the Shannon-Hartree theorem. So I hope you can all recognize this equation by now. So we have the C. This is our maximum channel capacity. SNR, this is the signal-to-noise ratio. And W is our bandwidth. So by bandwidth, we mean the difference between the upper and lower frequency over which we are allowed or we can transmit our signal. And basically, what this channel capacity equation means in practice. Okay, so I mentioned earlier on when we discussed the pulse code modulation that the pulse code modulation creates the need for certain amounts of bits per second, and that needs to be compared with the channel capacity. And of course, if we produce less bits than the channel capacity, we can hypothetically transmit without errors, right? However, if we, or to be precise, actually, with arbitrarily small amount of errors. Okay, now what you can see here, it's nothing more or less than just the previous equation. So we have the channel capacity in bits per second here, and this is plotted against the signal-to-noise ratio, which is on the horizontal axis, and there are some bandwidth value color coded. So basically, once your bandwidth increases, it will, push your communication towards in this direction, basically, right? So what you can see here is basically that if you really have a certain amount of information, there are of course two ways of transmitting that. If you need to increase your channel capacity, one is to try to use wider bandwidth, which is basically something we see is the most common case, or this is actually the most easy case. So for example, nowadays, compared to the initial Wi-Fi standards, there is a scheme which is called channel aggregation, where basically, so each Wi-Fi channel typically has 20 megahertz. However, if you need higher channel capacity, you can combine two 20 megahertz channel into one 40 megahertz channel, right? So this is exactly this principle here. By increasing the bandwidth, you increase your channel capacity, which allows you to transmit more information without more data without error. Now, then again, you can also operate using signal-to-noise ratio. So this is a little bit more tricky, but hypothetically, you could try to either reduce your noise by, for example, reducing temperature of your transmitter or receiver. Alternatively, you can try to increase the power, or in terms of radio systems or laser beam, you can also try to focus your energy by using directional antennas, or by using some lenses in the form of optical communication to focus your signal and boost your signal strength. We'll talk about that later on. Okay, now what is actually important here is that even for a noisy signal, right, you can still transmit some information. Okay, so basically this is So basically, as your signal deteriorates, in that case, even your signal to noise ratio is close to 0. You can signal to noise ratio close to 0 means actually you have much more noise than the signal, right? However, even for such a case, you can still transmit some information, right? Just very, very slowly. And if you think about this regime, even if you have a lot of noise, you can still try to increase the bandwidth of your signal to increase the amount of the capacity of your channel. Okay, and this might be actually quite intuitive, quite not so obvious, at least, that even if you do have a lot of noise, you can transmit you can transmit information, especially when you increase your bandwidth. Just, of course, it will impact the speed of your information. So I think in practical, this is now very rarely used, but back in around 2000, there was a very promising idea of using what was called ultra-wideband communication, right? And the idea was actually to allocate a spectrum from 3 to, well, I believe 12 gigahertz. So basically 9 gigahertz of bandwidth, which would allow communication of very weak signals, so below the noise level. However, because of the extremely large bandwidth, you could indeed use that to transmit information that was intended more for indoor applications. So communication between, wireless communication between your television and so on. And actually, theoretically, this concept did work. Actually, the problem was the cost of electronics for creating such a communication. The problem was that it's actually not that easy to create wideband processing signals. So, for example, if you think about the basic principle of the amplifier, that the wider the bandwidth of your amplifier, the lower the amplification, right? So there are basically practical problems with electronics. However, for some short period of time, it seems like a feasible. And there are some niche applications which still use this technology. However, I don't think it ever get to the commercial market, right? But anyway, even if you have a very weak signal with a lot of noise, so low SNR, you can still increase your bandwidth and send some information, again, errorless, because or with the limited or controlled amount of errors, because that's what we are actually looking for here. Okay. Okay. Now, another important thing is that what this Shannon-Hardy theorem tells you, that again, it only gives you a theoretical limit of what's possible and what's not. Okay. So similarly as with the entropy, it tells you what is possible. However, it doesn't really tell you how to achieve that. Okay. So again, this Shannon-Hardy theorem, it can be reached if you use perfect coding. Okay. So moving to the coding again, we go back to our linear block code. And this is a little bit a formal definition, right? So we have some sort of information word, which basically it's a key-long sequence, and then we convert it into an n-long sequence of inputs, where obviously the n is typically has to be greater than k. Right, and this is basically the schematic. So, it's really quite a simple concept. And the key block code parameters that we can actually measure is the redundancy. So this is the amount of added information here. So basically K, right? So K is the original length of the input of the code. N is the length of the output block, right? And simply by comparing the two, we can say what is the added redundancy. And contrary to that, we can also classify the efficiency, right? So those are the two contradicting parameters I was telling over the previous lectures, right? That the more redundancy, the less efficiency. Okay. And an interesting example of a PESEL number. Well, hopefully you all know that for those of you who don't know, like a PESEL is a Polish identification number. When you it's basically used for multiple reasons, including tax identification in Poland. And basically, this is 10 digits which contain different information. And the last digit is actually also some sort of error detection, right? So basically, it's not easy to mix or to do mistake with your PESEL number. And how it is done? Well, basically the Q value, so the Q is the last digit, is compared in this way. So each of the previous number is respectively multiplied by 1379, and then again. Then the result of that is 10 minus the last digit of the sum, right? So what you should actually pay attention here is that firstly it's a little bit more. So we are adding one more digit. So digits is a symbol out of the set of 10 10-letter alphabet, really, from 0 to 9, right? But this is not just a simple parity control. So each digit is multiplied by the number, so that also to avoid replacing the number. So for example, if you do the mistake by writing one digit before the other, this sort of error correction will capture that, right? And of course, over here we cannot use 2, 4, and so on, because then again that would create some problems in the mistaking. So this is actually really quite smart way of detecting error using a form of block code. In this case, of course, we just add one additional digit into the information contained between A and J. And if you want, you can actually calculate your own PESEL number, whether this checks and adds up. Okay. Now, what is important also is to see the distinction between systematic and non-systematic codes. So PESEL, and then the most intuitive case is the systematic code. So it basically means that we have the original bits that were added. The original input block, and we simply add either at the end or before that block this additional bit that create our redundancy, right? However, this is just an example, and in principle, we can have what's called non-systematic code, where we change, all of the values, right? So even here, you cannot really see your original input block, but still the information is there, just embedded with the additional redundancy bits. Okay, and this can sometimes be used to simplify the structure of coder and decoder. So I don't want maybe to go through this generator matrix here, but basically this is the way of generating the code, right? So the idea is that each rows form a basis for the linear code. So for a systematic code, you would actually see somewhere here a unitary portion of the matrix, right? Simply because this maps corresponding bits one by one. And then what is not unitary in the generator matrix, that's the added redundancy. Okay. And in general, of course, mathematically speaking, it doesn't really matter whether you use systematic or non-systematic code, in the sense that that the non-systematic code can be transformed with the systematic code with generally the same properties, right? So, okay. And I think over here we can actually conclude. So, are there any questions so far? No. Okay. Right. So I don't see anybody. I hope this is because everything is clear, not that because you're so confused that you don't even know what question to ask. Right. So again, I guess that concludes our lecture for today. Again, if you have any questions, feel free to reach me out over email or even writing a message here on Teams, even a private message. And then, well, with that, I would like to wish you a happy Easter break. And next time we see each other on Friday on the regular lecture. Okay, so well, thank you very much, and have a nice rest over the Easter. Thank you.
Thank you. Bye.
Thank you very much. Goodbye.
Bye.
Thank you. Goodbye.
Bye.